Thank you, and good late morning to everyone. I would like you to take a look out of the window now. What you see Lapland as today, well-developed, well-maintained industrial tourism. What you see in the picture of the screen is why I'm here speaking to you. You see the northern lights, aurora borealis. And now I would like you to take a look out of the window again and imagine that view over there 100 years ago. You saw a glimpse of that in the music performance yesterday. And I come from an institute which was established at that time, 100 years ago. I'll say a few words about the history because 1st of September this year we had the 100-year anniversary of the institute. Now the image you see moving there, that's the northern lights, aurora borealis. We are now flying in the space shuttle 300 kilometers above Finland and watching to the north. Now I don't have a laser pointer, but my finger is enough. This is the coast of northern Norway. We are now here. You see Greenland over there, an Arctic Sea, and the altitude is 300 kilometers. This is how the northern lights look like from space. And I want to say a few words about the history now. This is how the northern lights look like from ground. But the professor who established all this activity, I would say geospace environment research here today. His name is Professor Selim Lennström, and this is his statement about science. I think it's well said. Prejudice is destroyed with huge efforts. We break free of all the chains which keep us uneducated about the laws of nature. So what are the questions? Climate change, how can we forecast it? Ice-free Arctic Ocean, when? Which date? Can we say it? Of course not today exactly, but we aim for that. And now I want to say a few other words about Arctic, which normally are not really noticed, but which are very, very important for our technological society. We are living in the neighborhood of a star called Sun. Sun is not a light bulb giving steady light and energy. It's a hydrogen bomb. Now luckily, the visual light is only variable like 0.1% in the long time scales, so we get really stable energy in the form of visible light, but other forms of energy from sun, they are highly variable. This is a real picture of how we see a solar burst of material ejected into space. This material is electrons and protons, elementary particles, and we have a magnetic cloud, it carries magnetic field with it, traveling into the space in a few days towards Earth. Earth has this intrinsic magnetic field which actually protects us against the solar wind. Normally these particles go around, but at the polar regions, now this is important, Arctic and Antarctic, there's an axis. So you have either high energy particles in general penetrating down to the atmosphere, but also from the shadow side of the Earth. We have bursts of particles, like now you see an energy release in the form of northern lights, visual to us. But the northern lights, the visual phenomenon, is only 5% of all the phenomena occurring here. And the geometry of this magnetic field of the Earth, the geospace environment, this makes a huge difference to life on Earth. So I still want to say, currently today we would say geospace environment, that's the reason we are studying. And you see here a model, how Earth is like a stone in a stream of flow of water, and how dynamic is the situation around. Imagine you have to operate your satellites there, in that dynamic region. We sometimes have from sun bursts of particles, which simply just destroy the communication satellites, for example. Think about navigation satellites, which have to work. In the future, we want to drive our car into garage automatically with the Galileo satellite navigation. Professor Selim Lennström, I just want to say here, he wanted to make artificial aurora. So he built huge devices, tens of kilometers of power lines. And this is his drawing. He claims he was able to do it, but he was not able to photograph, so we don't really know. During the first international coordinated effort, 1882, he had 5 wooden cabins in Sodankylä for his measurements. But now, think about back, you go 100 years back in time and look out, you don't see anything. But in these regions, you might see 50 dwellings like this at that time. That was when Selim Lennström came to Lapland. That was how it looked like. Okay, now you can go look out from the window and go 100 years forward in time. What do you see? That's the interesting thing. I don't speak about history more. Some old pictures, I want to show one here. You see on the left a crowd of people, 1920s. Who are these people? So many. They are students. They are students visiting the Geophysical Observatory. And this I think is important. Even today, we have similar group of people. Like last Wednesday, we had 200 school children visiting us for one whole day. That was fantastic. Okay, today what we are an observatory which is part of University of Oulu, and we are the oldest scientific institute in northern Finland. And we employ about 40 persons, and FMI Arctic Research, as Osmo Alamo told, they employ about 30 persons. Altogether 70 people are employed by science in Sodankylä. Half of our people have academic degree, and I would like to mention that we have 2 research professors. Both of them are part of Centers of Excellence by Finnish Academy, different Centers of Excellence. Our budget is small, 2 million euros. 1/3 is from extra grants from EU and so on. And what do? We do basic scientific research, so we publish like 40 articles in the reviewed international scientific journals. Our policy, I'm afraid to say this, we don't publish in Finnish journals. Yes. And now I will say a few words. I don't go into too many details on what we do because time is clearly running. Do I have time until for like 5-6 minutes?
Yeah, let's say so.
Okay. So we have measurements in 20 different locations, from Spitsbergen to Ethiopia. And time is not enough to go to details. I will show one example which I think is, or 2 examples actually, are important. Like last night we had the northern lights here. We have, of course, in Finland cameras which photograph with the fisheye lenses the sky, but you don't do much with one single camera. What you need is a network of cameras, and together with FMI we are coordinating a network of magnetometers to measure magnetic field, optical measurements for the aurora, and this is better. You have a network of systems. But of course this is not good enough. What you need is a global network. From every lecture you should remember one thing. From my lecture, the magnetic field has changed in this 100 years its direction by 10 degrees. It's a lot. Of course we want to monitor the absolute field and the variations. We also monitor earthquakes. We have 4 stations, the blue ones. I show here the red ones now. We are adding more seismic stations. There are specific reasons for adding more. And I just show an example. Our own stations of course record like the North Korean nuclear explosion so that we can calculate where, in which depth and how large was the explosion. We are also able to set up, we have instrumentation to set up microseismic observations around mines, for example. This is something we want to do next year. And then we are measuring things like cosmic rays. We actually measure the secondary particles on Earth. And now we are expanding our network by setting up a station, our own instrument by Finnish financing, on the Italian station Concordia in Antarctic, not next season, but second winter from now. And that will be fantastic, at 3 kilometers height in Antarctic. Our main knowledge base is in radio wave remote sensing. Various radar systems, passive radio measurements, and I will just show one of them. The ASCAT infrared radars. Maybe somebody of you wants to understand why is it important to measure radio waves in the Arctic. I need to show the movie here. That's too high for a short man. But you see there a movie where Tromsø is on the right on the map, Helsinki is on the left, and the yellow area is free electrons at 300 kilometers altitude. And imagine all the GPS satellites. Their signal goes, it travels through the electrically conducting upper atmosphere. Its phase is affected. You see a phase curve on the left. And now when we measure phase curves of satellite signals, the black line is an orbit of satellite. In 20 minutes it flies above from horizon to horizon. We can use mathematical statistical inversion to make a tomographic image of the properties of the upper atmosphere. Now you see time running there. Every single night, the northern lights come from the north and create free electrons there. Every single day, sun rises and creates free electrons there. But you see waves. Atmosphere has much more waves than ocean. And you see that every single night with northern lights is different. Actually, your mobile phone, which has a GPS, has an inbuilt correction for the phase change in the atmosphere. But of course, it doesn't really work in these conditions. And of course, you can't drive your car into garage if the northern lights are there with even with Galileo. We need better technology for that, but I think we can solve it later. Now I need to skip a few slides. This is climate change and greenhouse effect. This would be interesting, but I will just want to say a few words about the technology we need to use if we want to understand the geospace. For example, we monitor the submarine transmitters. We just build cheap receivers, and when we have a network of those globally in the world, you see Sodankylä there as a red point, it's a receiver site. We can then monitor the upper atmosphere and near space. We use computer model tools. One of these lines is ozone, so we know what the northern lights are making to the ozone as example, as a prediction, and then we compare that with measurements. But our basic, most fantastic tool is the high power radars, infrared scatter radars, which we have here in the northern Scandinavia as a result of international collaboration, where 6 countries, Nordic countries and Great Britain, including then Japan and China, are financing the system. France, Russia, Ukraine, European Union are supporting. And we have these huge antenna dishes which are sending high power signals for remote sensing of the near Earth space. This is a bit old fashioned because you need some money to build these devices. And you can of course see, like the Chinese satellite which was destroyed by the missile, in the space debris distribution. You see the upper panels there are our measurements of space debris distributions from that. You can make a map of moon with a specific frequency. Why do we want to make a map of moon with the ASCAT radar, in this case with 600 meter resolution? Different wavelengths of a radio wave penetrate to different depths. And if you want to search for water, you need to search for structures. So you need to map with different wavelengths, as an example. We can follow the asteroids. You remember the Chelyabinsk meteoroid, which caused a lot of media attention. At the same time, we had 2 young men sitting there in Tromsø, monitoring the asteroid which passed 30,000 kilometers near Earth, very near. And they could follow that asteroid with our radar up to 300,000 kilometers distance. But in future we want to build the same thing, not with the antenna dishes. Instead, with modern technology, you turn the antenna and you can point to one direction. With having tens of thousands of antennas and clever electronics and modern today's fast electronics, you can sample all the antennas. And you can form 3-dimensional data products with multiple beams simultaneously. So instead of measuring in one point, you can actually measure vector velocities like vector winds in a volume. I'm soon exceeding my time, but I want to show this so that you understand how does it look. This is now an artist's view. This is not real at all, because we were telling the artist that we want to have 50,000 antennas. So he made a thing like this. The field is not eternal, it's limited, like from 70 to 300 meters in size. But what is our task is to measure the electromagnetic field. And instead of having the large mirror dish which reflects the field to one spot where it's amplified and then recorded, we can just simply record today all those antennas and afterwards calculate whatever we want to from the electromagnetic field by computers. So this is what we want to do in the future. This is more realistic view of the system. And this is a conceptual view, how would it look like in northern Scandinavia. We have several receiver sites. The receiver sites would have hundreds of simultaneous beams. Now we have just a few there. The green beam is the transmitter illuminator site, and you can steer that to 30-degree elevation electronically by facing the antennas. So there are no moving parts in the system. And now you can build, of course this is you need an engineer to make the real concept. This is how it looks like in a real concept. Very similar to radio astronomy. But no moving parts, and actually we have started to build it already to some prototyping. We just bought standard from Netherlands. Do we have anyone from Netherlands here? From Aston company, a radio telescope developed there, and we installed in Kilpisjärvi phased array system with 1,500 antennas. It's seen here, inaugurated in June this year, making 31 simultaneous beams towards the Tromsø illuminator. This is just to show you what is it to build research infrastructure. Some 40 trucks came from Netherlands, and of course University of Oulu and some EU regional financing was used to pay the bill, and then 2 summers with some workers, and it looks like building from Lego blocks. It's similar to building from Lego blocks, because in this case we want to use the passive radio astronomers receiver as a radar receiver for prototyping the Esa 3D technology. All right, one day the system was ready, and then we could measure. And the thing which we are measuring is that we make from Tromsø 2 megawatt radio power illumination, and we watch with 31 simultaneous beams from Kilpisjärvi, 80 kilometers away, and we see infrared scatter spectra as you see here in the panel. And that's a measurement of the future, which we want to do with the Esa 3D radar. This helps, of course, the whole global science facility or science community use new technologies, and this is international collaboration, but it also helps local companies to develop their technologies by implementing patents which have been developed for signal processing, for example. And we are, of course, in Sodankylä also coordinating some parts of the international education, and even having some financing from Ministry of Foreign Affairs to do that in Africa. But as a summary, I just would like to say that in Sodankylä there's a special scientific community which offers a platform of Arctic environment for setting up various instrumentation testing facilities, and also developing some industrial applications, in fact, from basic research to implementation. You can bring your own instruments, or you can rely on our instruments and our knowledge. And I just want to say something about the Finnish culture, because you saw yesterday some local style. This is singing 100 years ago. This is transforming knowledge from the past to the future in this singing. But they were singing about a specific device called sampo, which is something which nobody really knows. It's a treasure box, or it's a mill making you a fortune. It's displayed in the Finnish national epos Kalevala. I would just like welcome you to Levi once again and Finnish Lapland to find your sampo together with us. And that picture there is the Northern Lights last night, in fact. And you'll see the sampo of this region. Okay, thank you very much.
Thank you, Mr. Turunen. You really have, except sampo, you have the whole space in your hands and views here in Sodankylä. Are there any questions of this presentation? I think we got a lot of information this morning about Arctic technology, and I thank you very much. I give you also the tie for
I will bear it gladly. Thank you.
Thank you, and it's very nice to hear that you also teach the young people to learn about these things and what chances we have to learn about space and temperatures and also the Lappish hemisphere.